Section 250.30 A3 Exception number 2 of the National Electrical Code addresses the specific scenario of bonding the grounded conductor to the enclosure of a panel board downstream from the service equipment. This exception clarifies the permitted grounding and bonding practices within separately derived systems. It is crucial to understand this exception to ensure safe and compliant electrical installations. This code section focuses on separately derived systems, which are electrical power sources other than service equipment that derive their power from a transformer, generator, or converter. A key aspect of this exception is that it allows the bonding of the grounded conductor to the equipment grounding conductor at the source of a separately derived system. However, it prohibits this bonding at any point downstream from that source. The purpose of this restriction is to prevent parallel paths for neutral current, which can lead to several problems, including electromagnetic interference, voltage drops, and potentially dangerous currents flowing on the equipment grounding conductors. In a typical residential electrical system, the service equipment is where the main grounding electrode conductor is connected and the neutral conductor is bonded to the enclosure. This is the service bonding point. Downstream from the service equipment, in subpanels, the neutral conductor must remain isolated from the enclosure. The equipment grounding conductors provide the path for fault current to return to the source, allowing the overcurrent protective device, such as a circuit breaker or fuse, to trip and clear the fault. If the neutral conductor were bonded to the enclosure in the subpanel, it would create a parallel path for neutral current. Some of the neutral current would flow through the equipment grounding conductors back to the service equipment. This is undesirable because equipment grounding conductors are intended to carry fault current only, not normal neutral current. The flow of neutral current on equipment grounding conductors can cause voltage drops, which can affect the operation of sensitive electronic equipment. It can also create electromagnetic interference, which can disrupt the operation of other electronic devices. In addition, it can create a shock hazard if a person comes into contact with an equipment grounding conductor carrying neutral current. To avoid these problems, the National Electrical Code requires that the neutral conductor be isolated from the enclosure and subpanels. The equipment grounding conductors must be connected to the enclosure and provide the path for fault current to return to the source. Exception number 2 to Section 250.30 A3 specifically addresses separately derived systems, but the underlying principle applies to all downstream panels in a residential electrical system. The grounded conductor, or neutral, should only be bonded to the enclosure at the service equipment. This ensures that neutral current flows only on the neutral conductor and that equipment grounding conductors are reserved for carrying fault current. Consider a residential electrical system with a main service panel and a subpanel in a detached garage. The service panel is where the utility power enters the house, and it contains the main breaker, the grounding electrode conductor, and the neutral to ground bond. The subpanel in the garage is fed from the service panel via feeder cable. The feeder cable contains two hot conductors, a neutral conductor, and an equipment grounding conductor. At the service panel, the neutral conductor is bonded to the enclosure. The equipment grounding conductor is also connected to the enclosure. In the subpanel in the garage, the neutral conductor must be isolated from the enclosure. The equipment grounding conductor must be connected to the enclosure and to the grounding terminals of all the circuits in the subpanel. This arrangement ensures that neutral current flows only on the neutral conductor between the service panel and the subpanel. If a fault occurs in the garage, the fault current will flow through the equipment grounding conductor back to the service panel, causing the circuit breaker to trip and clear the fault. If the neutral conductor were bonded to the enclosure in the subpanel, some of the neutral current would flow through the equipment grounding conductor back to the service panel. This would create a parallel path for neutral current and could lead to the problems mentioned earlier. Therefore, it is essential to follow the National Electrical Code and ensure that the neutral conductor is isolated from the enclosure in subpanels. The equipment grounding conductors must be properly connected to the enclosure and provide the path for fault current to return to the source. Understanding and implementing proper grounding and bonding techniques are crucial for ensuring the safety and reliability of residential electrical systems. By adhering to the requirements of the National Electrical Code, electrical inspectors and installers can help prevent electrical hazards and protect people and property. When inspecting a residential electrical panel, one of the key things to look for is whether the neutral conductor is properly isolated from the enclosure and subpanels. If the neutral conductor is bonded to the enclosure in a subpanel, it is a violation of the National Electrical Code and must be corrected. The equipment grounding conductors must also be properly connected to the enclosure and to the grounding terminals of all the circuits in the subpanel. In addition to checking the grounding and bonding, electrical inspectors should also check for other common electrical violations such as loose connections, damaged wiring, and improper overcurrent protection. By performing thorough electrical inspections, inspectors can help ensure that residential electrical systems are safe and compliant with the National Electrical Code. In summary, Section 250.30 A3 A exception number 2 of the National Electrical Code prohibits bonding the grounded conductor to the enclosure of a panel board downstream from the service equipment. This is to prevent parallel paths for neutral current, which can lead to electromagnetic interference, voltage drops, and potentially dangerous currents flowing on the equipment grounding conductors. Understanding and implementing proper grounding and bonding techniques are crucial for ensuring the safety and reliability of residential electrical systems. Always consult the latest edition of the National Electrical Code for the most up-to-date requirements. In addition to the points already discussed, it's important to elaborate on the specific components and configurations that inspectors should be familiar with during residential electrical panel inspections, especially concerning grounding and bonding. Let's consider the components involved. Firstly, the service entrance conductors bring power from the utility transformer to the service equipment. These conductors are typically large gauge wires designed to carry the entire load of the residence. Secondly, the service equipment is the main control and distribution point for the electrical system. It typically includes the main breaker, which is a large overcurrent protective device that can disconnect all power to the residence. Thirdly, the grounding electrode conductor connects the service equipment to the grounding electrode system. This system can consist of a ground rod, a metal underground water pipe, or a concrete encased electrode used for ground. Its purpose is to provide a low impedance path to earth for fault current. Fourthly, the equipment grounding conductors are the wires or metallic pathways that connect the non-current carry metal parts of electrical equipment to the grounding system. These conductors provide a path for fault current to return to the source, allowing the overcurrent protective device to trip. Fifthly, the grounded conductor, also known as the neutral conductor, is the conductor that is intentionally grounded at the service equipment. It carries current back to the source under normal operating conditions. Sixthly, the ungrounded conductors, also known as hot conductors, carry the electrical current from the source to the load. Now, let's consider the common configurations that inspectors might encounter. A typical residential electrical system has a 120 volts/240 volts single-phase, 3-wire system. This means that there are 2 hot conductors, a neutral conductor, and an equipment grounding conductor. The voltage between the 2 hot conductors is 240 volts, and the voltage between each hot conductor and the neutral conductor is 120 volts. In the service equipment, the neutral conductor is bonded to the enclosure. This is the service bonding point. The equipment grounding conductor is also connected to the enclosure. Downstream from the service equipment, in subpanels, the neutral conductor must remain isolated from the enclosure. The equipment grounding conductors provide the path for fault current to return to the source. Another configuration is a separately derived system, such as a generator or a transformer. In a separately derived system, the neutral conductor must be bonded to the enclosure at the source of the system. This creates a new service bonding point. Downstream from the source of the separately derived system, the neutral conductor must remain isolated from the enclosure. Now let's delve into specific inspection points. Firstly, verify that the service equipment is properly grounded. Check that the grounding electrode conductor is properly connected to the grounding electrode system and that the connection is secure and corrosion-free. Secondly, verify that the neutral conductor is bonded to the enclosure at the service equipment. Check that the bonding connection is secure and that there are no signs of overheating or corrosion. Thirdly, verify that the neutral conductor is isolated from the enclosure and subpanels. Check that there is no bonding connection between the neutral conductor and the enclosure. Fourthly, verify that the equipment grounding conductors are properly connected to the enclosure and to the grounding terminals of all the circuits in the subpanel. Check that the connections are secure and that there are no signs of damage or corrosion. Fifthly, check for any signs of improper wiring or modifications. Look for loose connections, damaged wiring, and improper overcurrent protection. Sixthly, verify that all electrical equipment is properly grounded. Check that the equipment grounding conductors are properly connected to the equipment and that the connections are secure. Now let's talk more about common code violations regarding bonding and grounding that you may find. Firstly, missing or improper grounding electrode conductor. The grounding electrode conductor must be of the correct size and material, and it must be properly connected to the grounding electrode system. A common violation is using a grounding electrode conductor that is too small or that is not properly protected from physical damage. Secondly, improper bonding of the neutral conductor. The neutral conductor must be bonded to the enclosure at the service equipment, but it must be isolated from the enclosure and subpanels. A common violation is bonding the neutral conductor to the enclosure in a subpanel. Thirdly, missing or improper equipment grounding conductors. The equipment grounding conductors must be of the correct size and material, and they must be properly connected to the enclosure and to the grounding terminals of all the circuits. A common violation is using equipment grounding conductors that are too small or that are not properly connected. Fourthly, improper use of flexible metal conduit FMC or liquid-tight flexible metal conduit LFMC as equipment grounding conductors. FMC and LFMC can only be used as equipment grounding conductors under certain conditions. A common violation is using FMC or LFMC as equipment grounding conductors in situations where it is not permitted. Fifthly, using the neutral conductor as an equipment grounding conductor. The neutral conductor must never be used as an equipment grounding conductor. A common violation is using the neutral conductor to ground electrical equipment, such as a lighting fixture or an appliance. Sixthly, improper grounding of appliances. Appliances must be properly grounded to protect against electrical shock. A common violation is failing to ground appliances properly, such as by using a 2-prong plug on a 3-prong appliance. Electrical inspectors should be knowledgeable about these common code violations and be able to identify them during inspections. By identifying and correcting these violations, inspectors can help ensure that residential electrical systems are safe and compliant with the National Electrical Code. In addition to identifying code violations, electrical inspectors also play an important role in educating homeowners about electrical safety. Inspectors can provide homeowners with information about common electrical hazards and how to prevent them. They can also answer homeowners' questions about electrical safety and the National Electrical Code. By educating homeowners about electrical safety, inspectors can help them make informed decisions about their electrical systems and protect themselves and their families from electrical hazards. The National Electrical Code is a complex and ever-changing document. Electrical inspectors must stay up to date on the latest code requirements to ensure that they are performing accurate and thorough inspections. There are many resources available to help electrical inspectors stay up to date on the National Electrical Code, including continuing education courses, industry publications, and online forums. By staying informed about the latest code requirements, electrical inspectors can provide the best possible service to their clients and help ensure the safety of residential electrical systems. The grounding electrode system is a critical component of the overall grounding and bonding system. It provides a low-impedance path to earth for fault current, which helps to protect people and property from electrical shock and fire hazards. There are several types of grounding electrodes that are commonly used in residential electrical systems. Firstly, metal underground water pipe. A metal underground water pipe that is in direct contact with the earth for at least 10 feet can be used as a grounding electrode. However, the water pipe must be supplemented by another grounding electrode, such as a ground rod or a concrete encased electrode. Secondly, ground rod. A ground rod is a metal rod that is driven into the earth. The rod must be at least 8 feet long and must be made of copper, steel, or stainless steel. Thirdly, concrete encased electrode. A concrete encased electrode, also known as a U for ground, is a metal rod or wire that is encased in concrete. The concrete must be in direct contact with the earth. Fourthly, ground ring. A ground ring is a bare copper conductor that is buried in the earth in a ring around the building. The ground ring must be at least 20 feet long and must be buried at a depth of at least 2.5 feet. The grounding electrode conductor is the conductor that connects the service equipment to the grounding electrode system. The grounding electrode conductor must be of the correct size and material, and it must be properly protected from physical damage. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The National Electrical Code provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The grounding electrode conductor must be connected to the grounding electrode system using a listed connector. The connector must be suitable for the type of grounding electrode being used. The grounding electrode conductor must be protected from physical damage by being installed in conduit or by being located in a protected area. Proper installation and maintenance of the grounding electrode system are essential for ensuring the safety and reliability of residential electrical systems. Electrical inspectors should carefully inspect the grounding electrode system during inspections to ensure that it is properly installed and maintained. Now let's talk about surge protection in residential electrical systems. Surge protective devices, or SPDs, are designed to protect electrical equipment from voltage surges, which are sudden increases in voltage that can damage or destroy electronic devices. Voltage surges can be caused by lightning strikes, power outages, or other electrical events. SPD work by diverting the surge current to ground, preventing it from reaching sensitive electronic equipment. There are several types of SPD that are commonly used in residential electrical systems. Firstly, whole house surge protectors. Whole house surge protectors are installed at the service equipment and protect the entire electrical system from voltage surges. These devices are typically hardwired into the electrical panel and provide protection for all circuits in the house. Secondly, point-of-view surge protectors. Point-of-view surge protectors are plugged into electrical outlets and protect individual electronic devices from voltage surges. These devices are typically used to protect computers, televisions, and other sensitive electronic equipment. The National Electrical Code requires that SPD be installed in certain locations, such as at the service equipment and at separately derived systems. The code also specifies the minimum performance requirements for SPD. When selecting an SPD, it is important to consider the following factors. Firstly, surge current capacity. The surge current capacity is the maximum amount of current that the SPD can safely divert to ground. The surge current capacity should be high enough to protect against the expected voltage surges in the area. Secondly, voltage protection rating. The voltage protection rating is the maximum voltage that the SPD will allow to pass through to the protected equipment. The voltage protection rating should be low enough to protect sensitive electronic equipment. Thirdly, response time. The response time is the time it takes for the SPD to begin diverting surge current to ground. The response time should be fast enough to protect against fast rising voltage surges. Fourthly, listed. SPD should be listed by a recognized testing laboratory, such as Underwriters Laboratories UL. Proper installation and maintenance of SPD are essential for ensuring that they provide effective protection against voltage surges. Electrical inspectors should verify that SPD are properly installed and maintained during inspections. Remember to always consult the latest edition of the National Electrical Code for the most up-to-date requirements regarding surge protection. Finally, let us discuss arc fault circuit interrupters, or SIs, and ground fault circuit interrupters, or GFCIs. SIs are devices that are designed to protect against electrical fires caused by arc faults. An arc fault is an unintentional electrical discharge between two or more conductors. Arc faults can generate high temperatures, that can ignite flammable materials such as wood, paper, or fabric. ASSAIs work by detecting the unique characteristics of arc faults and tripping the circuit breaker to interrupt the flow of electricity. The National Electrical Code requires that ASSAIs be installed in certain locations such as bedrooms, living rooms, and dining rooms. The code also specifies the performance requirements for ASSAIs. GFCIs are devices that are designed to protect against electrical shock. A ground fault is an unintentional electrical path between a conductor and ground. Ground faults can occur when a person comes into contact with a live wire or a wet surface. GFCIs work by detecting the flow of current through an unintended path and tripping the circuit breaker to interrupt the flow of electricity. The National Electrical Code requires that GFCIs be installed in certain locations such as bathrooms, kitchens, and outdoor areas. The code also specifies the performance requirements for GFCIs. ASSAIs and GFCIs are essential safety devices that can help to prevent electrical fires and electrical shock. Electrical inspectors should verify that ASSAIs and GFCIs are properly installed and maintained during inspections. Here's a more detailed explanation of the differences between ASSAIs and GFCIs. Firstly, function. ASSAIs protect against arc faults, which can cause fires. GFCIs protect against ground faults, which can cause electrical shock. Secondly, how they work. ASSAIs detect the unique characteristics of arc faults, such as erratic current flow. GFCIs detect the difference in current between the hot and neutral wires. If there's a difference, current is leaking to ground. Thirdly, where they are required. ASSAIs are required in many areas of the home, including bedrooms, living rooms, dining rooms, and family rooms. GFCIs are required in areas where water is present, such as bathrooms, kitchens, and outdoor areas. Fourthly, testing. ASSAIs and GFCIs should be tested monthly to ensure that they are working properly. To test an ASSAI or GFCI, press the test button on the device. The device should trip, interrupting the flow of electricity. If the device does not trip, it should be replaced. Electrical inspectors should be knowledgeable about the requirements for ASSAIs and GFCIs and be able to identify them during inspections. By ensuring that ASSAIs and GFCIs are properly installed and maintained, inspectors can help protect people and property from electrical hazards. Also note that combination ASSAI/GFCI breakers are available, which offer both arc fault and ground fault protection in a single device. These are becoming increasingly common and can simplify wiring in some situations. They are often required in new construction or when replacing existing breakers. When inspecting electrical panels, always look for the labeling of circuits. Each circuit breaker should be clearly labeled to indicate what it controls. This is important for safety and convenience. If a circuit breaker trips, you need to know which circuit it controls so you can troubleshoot the problem. If there are no labels, or if the labels are unclear, this is a code violation. The labels should be legible and durable. Handwritten labels are acceptable, but they should be written in a permanent marker that won't fade over time. Pre-printed labels are also available. In addition to the circuit breaker labels, the panel itself should be properly labeled. The panel should have a label that indicates the voltage of the system and the maximum current that the panel can handle. This information is important for safety and for determining whether the panel is adequate for the load that it is serving. Overall, residential power panel inspections require a thorough understanding of the National Electrical Code, as well as knowledge of common wiring practices and potential hazards. Inspectors play a vital role in ensuring the safety and reliability of electrical systems, protecting homeowners from electrical fires and shocks.